Thanks, everyone. Welcome back. So let's start with the afternoon session. We have two excellent panels in the morning, from personal assistant to the robots. Now in the afternoon, we are going to hear about the deep learning breakthrough, the video understanding, autonomous driving, and computer games. So you are in for a big treat. Now, let me introduce our speaker for this session, who is Lukasz. And Lukasz has been our speaker last time. How many of you were in our conference last time? All right, I see quite a few hands. And last time, Lukasz talked about Lukasz is from Google Brain team, and he talked about how deep learning can be applied to natural language processing that becomes a reality now. But today, he's going to talk about how one model you learn from image, speech, and language processing can apply to another domain so that you can switch domain and back. And that's something very amazing. Let's welcome Lukasz.
Thank you. So I will talk today about our first steps in research. So I'm in the research part of Brain. About the first steps we are taking to address one problem that I think many people that look at the state of AI today see, and that is that deep learning is great, but it's always for a single task. It's great at image classification, it's great at translation, it's great at a number of things, but how about doing them all? How about something more general? So we are taking first steps to make a model that could really solve a number of tasks simultaneously in one go. And thank you. So the first question you need to ask yourself is, why do you want one model? I mean, we might have this dream of a general AI, of something that just works like a human, but more concretely, we need some more practical reasons to do a single model. So when you're trying to make a single model to solve a number of AI tasks, and by a number I mean image recognition, image generation, text generation, translation, speech recognition, all of these tasks that we have. So when you try to do one model for all of that, you have some problems. Like, it takes a long time to train, because you need to train it on all of that. It takes a lot of effort to actually get good results. So what are the gains? And there are a few. The first gain is something that people call transfer learning. And the point is, normally, you might have very little data for some new task. You might go on and gather this data, but what if you could just use all of the knowledge of images that's in ImageNet, of translation that's in the existing data sets? So what we actually can demonstrate is that this model, you train it on these large available data sets, and then you have a new task that has much less data, and it does much better. So that's one advantage. And the other advantage is when you train one model for a lot of tasks, you can do a lot of tuning and optimization once. Maybe you can deploy it on a device, and the model is there, and you don't need to repeat this process so many times. So these are our goals, and we made some first steps. We have some models that work. We are improving them. So let me tell you how is this model built? How do we achieve this? And the main idea is that the model has a shared core. So it's a little bit like people imagine the brain. You will have some things that processes images a little bit, something that processes sound, something that processes text. We call this a modality. It's a very small network. And the biggest part in the middle is shared between all tasks. So in the middle, you have a representation that's shared for text, for images, for audio. and the parameters of the model are shared between these tasks. So now, to make this insight of this model, you need to give it enough power, enough deep learning power to actually solve these various tasks. And we found that there are 3 key blocks to make this model work. And these are convolutional layers, attention layers, and mixture of experts layers. So I'll start with attention, because that's, I think, something where we've made most progress this year. So an attention layer, so this was supposed to be a picture showing it. Anyway, an attention layer is a layer that allows a query to look at a memory value that's been stored before. So if you have a query, for example, a word in a sentence, an attentional layer can look at everything you've seen before and give a return a summary of what's happened there. Then convolutional layers, I think they're well known, but we've improved them with something called depth-wise separable convolutions, which is a generalization of an architecture called inception, known in image recognition before. And in this way, you can have far less computation and get better results. And then the third block is a mixture of experts layer. In a mixture of experts, instead of having like one matrix that you multiply by, you have a number of matrices, maybe 100, and you select which one of them you actually want to multiply by. So in this way, you maybe multiply by 2 or 4 of these to compute, but you have a large number of parameters. So this allows your model to have a lot of capacity without performing a lot of computation in every step. So these are the basic blocks, but you can say, okay, so there are new blocks in deep learning every few months. What do we get? So first, we try these blocks, right? We say, if we use these blocks rather than what was there before, do we get better results? So the depth-wise separable convolutions are an oldest block. This has been done like a year ago. And you can see that applying them improves image recognition accuracy. It improves it actually with lowering the computational cost. And the mobile nets that were mentioned in the morning here are also using depth-wise separable convolutions. So the next block, the mixture of experts, has also been tried. And the task it's been tried on is language modeling, where people measure perplexity. And if you can see this table, you'll see that it goes down by a significant margin, like by 1/3. And at the same time, you're paying less in computational cost again. And for attention, so these are results, these are recent results that we had this year. I presented here last year some translation results, and they were a big breakthrough compared to previous non-deep learning translation systems. And it's very pleasant to come back here and tell you that the results are, again, better by the same margin. So the blue score is a standard way to measure translation quality. And previously, we got to like 25 on the English-German task. And we thought that's great because earlier systems were about 20, and human translators get about 30. So this year, we are at 28.4. And actually, just yesterday, there was a paper where it's 28.9. So we're very fast approaching the level where this metric will be at the same level as human translators. Okay, so we have great numbers. We get very good numbers with the same or lower computational budget. But what does this mean? Like, the numbers are great for scientists, but how can you see that these models are actually better? So for machine translation, this is an example I like very much. you know, translating sentences with machines has been around for a long time, but there are some tricky sentences that really require some knowledge of the world, some understanding to translate. And they're known as Vinograd schemas. For example, when you say the animal didn't cross the street because it was too tired or because it was too wide, the it will refer either to animal or the street, and in French or German, you need to use a different gender for translating it. So now, all translation models before, they failed on one of these sentences, because they didn't really have the knowledge to distinguish what the it was referring to. Our new models, finally, not on all sentences like that, but on a number of them, make the right choices, and we can actually look inside the model and see that it puts the attention mask on the right word. So we can finally see that it has some understanding of sorts of what the it refers to. And then it translates correctly, and it translates better. Then we applied the same model, an attentional model that generates sequences, to generating images. And generating images has been a large field recently. There are adversarial networks, and a lot of people work on it. So we made the following test. We generate some faces and ask people, is this a generated face or a real photo? And the previous networks, they could fool people maybe 8% of the time, maybe 11% of the time. So our networks can now fool people almost 40% of the time. And the real photos would be 50. So we're very close to generating photos that really look like real faces. And again, last week, there have been even newer papers. So generating text, generating images is really doing well. Translation is doing well. How about generating long text? You know, translation works sentence by sentence. You want to generate one sentence, that's okay. How about if you needed to generate an article? So we did the following. We took all of Wikipedia, and then for every Wikipedia title, we took the search queries and reference web pages. So this is a lot of material. It's like 100 pages for every article, and then said, please take this and summarize and generate the article. And the results, they're really good. If you ask about a person, you get a summary of what this person has done in life. Everything the internet knows, you can see it and get it generated by the model. Of course, it's not perfect. It's research. But I think it shows that these models are really getting to capabilities that were not there before. And finally, we want, as I said, we want to put it all together, so we trained a model that does a number of these tasks together. So this model was trained on 8 tasks jointly. It can translate English to French and French to English, English to German and German to English. It can recognize speech and change it into text. It can parse text into parse trees, and also classify images. So, of course, we would like to do even more tasks, but for research purposes, we did these 8. And this model actually does pretty well. It does slightly worse than the best models we have for every task, but it can actually perform very reasonably on all of them. And I think that shows us a path to making models that really generalize to a large number of tasks. So now you might ask, okay, so this is interesting research, but at this conference, I suppose a lot of people work for startups or are planning. So how does that affect me? You have this one big model, but it takes a long time to train. It does a lot of tasks, but I maybe care only about one task. So what is in there for me? And as we develop this research, we're also thinking, how can we help other people? How can we make it useful in the meantime, before this really gets used by everyone. So we made this open source repository. You can see the link on the slide. And this repository has all our baselines, meaning state-of-the-art models for translation, summarization, parsing, a lot of different problems that we considered. It has state-of-the-art models for image recognition, classification, and we wanted to make it easy to use, and that's often a very hard part with deep learning frameworks. So we decided to go the open source route, take a community, and indeed, there are now more than a dozen contributors that really contribute code every day. They tell us, look, this is too hard to use, this I cannot train, and then they add changes to make this really live and be useful. And soon we are planning to release pre-trained models, so you could just grab a model and translate things or summarize things for yourself. So I consider this an important part of building the large, more general models, that it's not just that Google can do it, but that we can all participate in it. And one reason I consider this so important is when you think a little bit about the future. So we can generate images that fool people 40% of the time. They think they're real. In a year, maybe in 2, what if we can generate videos? What if we can say, please take someone's face and generate a video of him saying something? If you think fake news are bad today, then when this comes, they'll get much, much worse. If this is possible, then it should at least be possible and open to everyone. And in the longer run, if we have a really general model, can generate images, videos, text, does this model understand the world? Does it really give us something more general than the specific intelligence we have now? It's very hard to answer now, but we are on a path, and maybe in a few years we will be able to say more. Thank you.